Hello folks, in this video we're going to talk about how we can use what we know about arc length to determine what we call the linear and angular speed of something moving along a circular path. So just some definitions. Linear speed, if you've taken physics, shouldn't be too familiar or too unfamiliar. It's really just the same thing. So how far something went divided by the amount of time it took. Angular speed is very similar. It's just instead of measuring how far it went over some amount of time, we're measuring the angle that was swept out. And this will make sense, I think, once we do an example. So let's just jump into one. Alrighty, here's our example. And so what we have here is I've drawn a circle kind of looking at it from an angle. So that's why it's not circular, at least from our perspective. So in this case, you have a tiny circle, or maybe it's a big circle, where the radius of that big black circle is 50 centimeters. And the radius of this smaller red circle, which is concentric, so it's the same center, is 20 centimeters. So that's right there. Alrighty. Now, I'm just going to imagine that you have a tiny person on the edge of the black circle and on the edge of the red circle, right there. And let's just pretend that this circle rotates, so this person moves up. Let's say they rotate, just to make it our lives a little bit easier and not make it too crazy. Let's say they move 45 degrees. And so from our perspective, it's not going to quite look like 45, but that'll look like that somewhere. So this angle right here, theta, equals 45 degrees. And so now this guy, this little stick person, is over here. Okay, so he went from here to here. And let's say that rotation took how long? Let's suppose let's just say 10 seconds. Ready? Now remember, these two circles are in the same, the red circle is just drawn on top of the black one. And so pretend this is like a lazy Susan at like a Chinese restaurant, where you spin one and then you're looking at, you spin it, and pretend that you're looking at something on the outside moving along, and then something that's further inward moving along. That's kind of what I was getting at. And so if that's the case, then, well, since this is the same circle, it's not the same rotating object, if the black circle is rotated 45 degrees, so does the red one. And so actually, the red one is also going to move 45, which would end up, I don't know, might look something like that. And I'll draw that here. And so this red stick person goes from here to here. So that angle is also 45 degrees. So this is something to note. Even though they're different sizes, they actually go through the same rotation because they're on the same circle. Okay, so let's talk about angular speed since we're already here. And so the angular speed, by the way, this little letter right here, that's little omega. Again, it's Greek. In case you're curious, big omega, so capital omega, is the headphones, the ohms. It looks like this. If you're familiar with comics, then this is the symbol of Darkseid because he shoots the omega beams. But that is neither here nor there. Now, our angular speed then, our omega, and this would be for the red and the black one, both red and black. Well, that would just be, 45 degrees divided by 10 seconds. Or just 10s. Okay, that's not usually how you define or how you report angular speed, though. Usually, you'll report it as revolutions per minute. Alrighty? And the reason this is the case is, well, I don't really know, actually. But it's just kind of the most common way to say it. So let's actually do that. Okay, so what I'm going to do, well, let's see, there's 45 degrees in this rotation. But again, one revolution meaning going all the way around, revolution, well, that would be 360 degrees, right? So 360 degrees to get from here all the way back to where you started. Okay, if that's the case then we can kind of keep this in mind as we do our unit converting. So there's 45 degrees. If I want to get rid of my degrees and end up with revolutions, do a little bit of dimensional analysis here, I'm going to want to multiply it by 1 revolution over 360 degrees. And now we can see how our degrees will undo each other right there. Last part, we need to get from seconds to per minute if I want to report it in RPMs. And so that, well, there's 60 seconds in a minute, so 60 seconds equals 1 minute. And therefore, I need to multiply, by, let's see, I have seconds in the denominator here. So if I want to get rid of the seconds, I need the seconds on top now. So that'll be 60 seconds per 1 minute. And now we can work our calculator magic here. Seconds and seconds, degrees and degrees cancel out. And that leaves us with, let's see, 45 divided by 360. I'm going to use Mr. Calculator here. Okay, actually, realize we don't really need our calculator here. Because, let's see, 60 over 360, and then, let's see, that'll be 45 over 10 times 1 over 6. Which would then come out to 45 over 60, or my computer's being troublesome here, I apologize, 3/4 revolutions per minute, or just 3/4 RPM, you could say. Revolutions per minute or RPM. Okay, we also could have done it with radians instead of degrees, and we should have got the same answer, so this is going to be interesting. Notice here, 45 degrees, and check my work here, but 45 degrees is actually pi over 4 radians. I'm going to put radians in parentheses because radians, again, is a kind of dimensionless unit, so we don't really need to write it at all. But then I would say, okay, omega, our angular speed, would be pi over 4 radians in 10 seconds. Again, all that means is that it sweeps out an angle of pi over 4 radians in 10 seconds. But again, now, 1 revolution, instead of saying it in 360 degrees, I need to put on my radian glasses and say, oh wait, it's not 360 degrees, it's 2 pi radians. And so now, instead of 1 revolution per 360 degrees, it's 1 revolution per 2 pi radians. And now, we still have to multiply by our time. So that would be 60 seconds per minute. And hey, look at this. Pi and pi are going to cancel out right there. And on the bottom here, well, let's clean this up. So I could bring this 4 down bottom there. So I'll end up with 60 seconds. Oh, sorry, seconds will cancel. So that's 60 revolutions per, that would be 4 times 10 times 2 over 80 minutes, but if I simplify this, that'll end up being 3/4 RPM as well. So it actually doesn't matter if it's radians or degrees for angular speed. So let's take a look now at an example of calculating linear speed along this circular path. So we go back over here, notice we need to figure out then, okay, in 10 seconds, these two folks went right around here on this yellow path, and this guy went around this yellow path. So we know it took 10 seconds, but we have to know how far they went. It's a little bit trickier than maybe you normally seen it in your physics class previously, because you're not going on a straight line. But that's not so bad, because we now know how to calculate the arc length of a circle. So if I take a look at, I shouldn't have used yellow for both of them. Let's look at the black circle. So the black circle, if I kind of blow it up here, again, it's got a radius of 50 degrees. Sorry, 50 centimeters. And the angle that was traced out was 45 degrees. But I'm going to use radians here because it makes our lives easier if we remember our arc length formula. So arc length, remember, if I just convert it to radians, is actually just r times the angle, assuming that this angle is in radians. right? I'm not going to go through why that works because we had talked about it in class. But if that's the case, well, then our arc length is just 50 centimeters times, let's see, 45 degrees is pi over 4. We had just figured this out. It's right there. Times pi over 4. And this is going to give us our distance that we've traveled. So let's see, that'd be 50 pi over 4. So I'll just say 25 pi over 2 if I simplify it. Now notice the red circle, well, it's smaller, obviously. So it's the same angle, theta, but since it's a smaller radius, then this person on the red circle traveled less distance, and that should make sense. So in this case, our arc length, which again we've been using S, I should call that S, is again R times the angle, again in radians. And so in this case, it's going to be 25 centimeters times pi over 4, which is, in this case, it's going to be, well, 25 pi over 4, as opposed to 25 pi over 2. And now, I just need to take that length, or that distance, and then divide by the amount of time. And so I'm going to use a fancy V for linear velocity. V, that's how I write it. It's like kind of my cursive V, essentially. For the black circle is, well, it'd be S divided by time. So in this case, it's just 25 pi over 2 divided by 10 seconds. Now remember, I should have said this before, don't forget units on this one. So since our distance was measured, well, we used our radius, which was given to us in centimeters, our arc length is centimeters. And this is why radians is a dimensionless unit. There's an explanation as to why radians, you kind of just ignore the units, is because it's not, in its definition, it actually is kind of a ratio, in which case you divide the units out, and we just call the result a radian. If you want to do some more research, I totally welcome you to. But I'm going to ask your forgiveness in the hand waving, which I don't usually like to do. But in this case, we'll just have centimeters right there. And this just ends up being, let's see, 25 pi over 20 centimeters per second. And if I simplify this, it's actually 25. If I simplify this is simply 5 pi over 4 centimeters per second. If I follow suit with the red one, then our velocity, in this case, 25 pi over 4 centimeters, took us 10 seconds to get there. So that'll be 25 pi, over 40 centimeters per second, which simplifies to 5/8 pi. So that's how you can use angular and linear speed to figure out where your person moved and how fast they went, or how fast your circle rotated.